Hello, my name is Joshua from AGHAMALAYAN, and today I'm going to discuss about reaction rates and stoichiometry. The first thing that comes to students' minds when it comes to reaction rate and stoichiometry are the numerous calculations that makes this topic really difficult. But actually, it's not that difficult. The difficult portion is that the students miss a lot of vital information about how will these problems be interpreted. That is why, before we immediately dive into the pool of computations, I'm going to discuss the general information about reaction rates and stoichiometry first. So the reaction rate of a chemical reaction tells us how fast does the reaction proceed. It is usually expressed in the unit of molarity per second, and it is the change in the concentration of a reactant or a product over time. Say a given chemical reaction of A plus B, which yields to C. So we also have their respective coefficients. So how do we express the reaction rate expression for this one? So rate is equals to the negative reciprocal of the coefficient of the first reactant, which is A, multiplied by the change in the concentration of A over the change in time. Since we know that the reaction rate is change in concentration over change in time. This is also equals to the negative reciprocal of the second reactant, which is B, multiplied by the change in the concentration of B over change in time. And this is also equal to the reciprocal of the coefficient of the product, which is C, multiplied by the change in the concentration of C over change in time. So what can we deduce and infer from this chemical rate expression of this chemical reaction? So first, when we write the expressions for the reactants, the sign is negative. Why is this so? We know that for a chemical reaction to proceed, the reactants are being consumed and the products are being formed. So whenever we write reaction rates, we must pay attention to the sign. For the reactants, it must be in the negative notation. For the products, it must be positive, since we know that as a reaction proceeds, the products are being formed. So the notation for that must be in positive sign. Another thing we have to take note in here is that the coefficients of the chemical compounds in a chemical reaction also matter, since, as you can see, we multiply the change in the concentration over change in time with the negative reciprocal for the product, for the reactant, and positive reciprocal for the product. Now, let's try some examples. Consider the reaction of the decomposition of calcium carbonate given by the reaction CaCO sub 3, which yields to CaO plus CaO sub 2. Suppose that at a particular moment during the reaction, calcium carbonate is being decomposed at a rate of 0.077 molarity per second. At what rate is calcium oxide being formed? So everything seems complicated at the start, but let's break down into what we have, into what we are finding. So we have the rate of the decomposition of calcium carbonate, and we are asked of the calcium oxide. So we are finding for this one. So now let's write first the rate reaction expression for this kind of chemical reaction. So with that, we have rate is equals to the change in the molarity of calcium carbonate over change in time equals to the change in the concentration of calcium oxide over time, which is actually equal to change in the concentration of carbon dioxide over change in time. Okay, so now we have the rate expression. So we are given with the rate of calcium carbonate, which is 0.077 molarity per second. So we have this one. This is 0.077 molarity per second. And we are finding the rate of calcium oxide being formed, which means we are finding this one. So remember, this is in negative notation. So how do we compute for that? Since only the two chemical elements are involved, we are not going to pay attention to the CO2 anymore. So, like what I wrote earlier, we have change in the concentration of calcium carbonate over change in time equals change in the concentration of calcium oxide over change in time. We know that since calcium carbonate is in the reactant side, it must be in negative notation. So we have 0.077 molarity per second. And since this is the decomposition rate for calcium carbonate, it must be in negative notation. So in order to find the decomposition, the rate of formation of calcium oxide, we have to multiply this number with negative 1. Why? So that we will yield with a positive number. Doing so, we have 0.077 molarity per second. And now this is the rate of the reaction for calcium oxide formation. Seems easy, isn't it? But not all chemical reactions have this 1:1 ratio. So later we are going to try another example which does not come in a ratio of 1:1:1. Let's try this another example. The formation of ammonia is given by the chemical reaction N plus H, nitrogen gas plus hydrogen gas yields two molecules of ammonia. Suppose that the nitrogen gas at one particular moment of the chemical reaction is reacting at a rate of 0.045 molarity per minute. The question is, at what rate is ammonia being formed? So now that we have different coefficients for each of the chemical elements and compounds involved in a chemical reaction, we can easily assume that 0.045 molarity per minute also applies to ammonia. So the first step that we are going to do now is to write the rate expression for the whole chemical reaction. The rate expression for the whole chemical reaction is rate equals the change in the concentration of nitrogen gas over change in time. This is in negative. This also equals to the negative 1/3 multiplied by the change in the concentration of hydrogen gas over change in time. So why is this negative 1/3? So as I said earlier, we are going to get the reciprocal of the coefficient of the element or the chemical compound that we have in a chemical reaction. And since hydrogen gas is a reactant in this chemical reaction, it must be in negative notation. This is also equal to positive 1/2 multiplied by the change in the concentration of ammonia over change in time. So since ammonia is in the product side, it must be in positive. So now that we have the reaction rate expression, we are going to find the rate of ammonia being formed. What we have here is 0.045 molarity per minute. This number for the nitrogen gas represents this. So because we know that the nitrogen gas is at the reactant side, it must be in negative. So this 0.045 molarity per minute must be on a negative notation. Negative 0.045 molarity per minute. And since we also have another negative sign on the expression, we are going to multiply this again by negative 1, which will give us 0.045 molarity per minute. So now we have a positive answer, and that corresponds to the logic that we have, that if we are talking about the reaction rate of a product, it must be on a positive notation. So next, we are just finding for the change in the concentration of ammonia over change in time. We are not including 1/2. So what we are going to do is that we are going to divide 0.045 molarity per minute to 1/2, or basically you can just multiply it to 2. This gives us 0.09 molarity per minute. And now we have the rate of ammonia being formed. So that's it. I hope reaction rates and stoichiometry become quite easier now. Thanks for watching. Do not forget to subscribe to our YouTube channel AGHAMALAYAN and click the bell to subscribe. Click the bell button to receive updates when we post new tutorial videos. This is Joshua Geraldino. Thank you very much.